Let's do a little quiz on your homework. So this quiz is kind of to see in the big picture if you're catching on to what's going on. So here's question number 1. So everyone's thinking for themselves. So on the first day we said that calculus is really about 2 goals. You know how much of something you have, and you want to know how fast it's changing. Or you know how fast something is changing, and you want to know how much of it you have. The first question is, which of these statements summarizes what we've been working on recently in the course? A or B? Which of these statements summarizes what we've been working on recently? A or B?
Recently in the last 2 days.
It doesn't matter. There's only one kind of recently. There's only one of these 2 things so far that we've worked on in the course. How about that? There's only one of these 2 things that we've worked on so far in the course. Okay, good on this one?
Yes.
All right. So here we go. So in this question, you're going to summarize the process we're learning related to the answer you just made in number 1. Okay? So suppose you're given a graph showing kilometers squared per day of oil on the ocean surface as a function of time and days since an oil spill accident. Okay? So the overall question is, what's the overall goal in this situation, according to what we've been learning? And then outline the steps involved in achieving this goal. So we're trying to see if we're catching on or not to the big picture. Okay? Go. So what's the goal in a situation like this? Relative to what we've been doing, okay? And then outline the steps involved in achieving this goal. I'm going to have some of these. If you don't get yours, I'll give it to you later. Is Jacob here today? Chen. Samantha. Peter. Peter. Here. Heidi Fang. Chen-Rui. Anthony. Nietzsche. Wrong one? Oh, it's right behind you. Sorry. Good? Jacob, you good?
Yep.
Okay, like 1 more minute. Okay, let's turn the homework in. You can finish writing what you're writing. If you're done, hand it up. Yes. Yeah, you always, whatever is assigned, you always put those all together. Unless it's something you're emailing. For that, you need to do again. What's that?
Lauren.
R, yeah.
Well, there's two. There's Lauren and Ryan.
Oh, Reabula? Okay. What have we been working on? A or B? You know how much of something you have and you want to know how fast it's changing, or you know how fast something is changing and you want to know how much of it you have. So this is a good kind of wake-up call if you don't get this one right, okay? The answer is B. Okay? We've been given, starting with what? Starting with a rate of change function, right? Starting with a rate of change function. And so what's the goal in this situation? What's the goal in this situation? Sharon?
To find out how far that was, like the total distance.
Kind of, not distance, but
Little area.
yeah. And so there's a kind of a key word to this to answer this question. Accumulation of area of oil. Our goal is to find the accumulation of the area of oil, or even more specifically, an accumulation function, meaning how much has accumulated at any given time in days. How much has accumulated? So that's our goal. We know how fast it's changing, and we want to know how much of it we have. Right? Right. So that's accumulation. So whether that's an amount of accumulation, say at 3 days, or that's a function of accumulation, meaning the function would tell us how much is accumulated at any point in time. Okay? So that's our goal. The accumulation of, in this case, area of oil on the ocean. Okay, first step in this process of figuring out, for instance, the accumulation function. So suppose we want the accumulation function. First step, yeah, Autumn.
So you're going to want to find delta x, so you make like intervals.
Okay, great. All right, yeah, we're gonna start with intervals. So maybe we'll do 0.2. Okay. And why are we, somebody else, why are we breaking it up into intervals? For what purpose are we going to start by breaking it up into intervals? Corey?
Because you don't have a constant rate of change, and so we're going to treat it as constant rate of change in those intervals.
He says we don't have a constant rate of change, and we want to treat it as constant rate of change in each of those intervals. What do you think? Yeah, right on the mark. Okay, so we look at this first interval, and we want a constant rate of change. Do we want a constant rate of change of 10? 20? 50? What's our purpose in picking a constant rate of change in those first 0.2? So what are we trying to do by picking a certain constant rate of change? Somebody new? Yeah?
It's going to approximate the actual rate of change.
Yeah, yeah. We want the constant rate to be something like the actual rate. Okay, so what about, so 20? Reasonable? Little low, but reasonable. What about 25? Would that be a valid approximation? 27? 29? Yeah, so all of those, any of those would be kind of in the ballpark, and that's what we're doing. We're trying to find a ballpark constant rate based on the actual constant rate. Okay, but then we have some kind of systematic methods of picking that constant rate. How do we systematically do that, rather than just eyeballing each one? Yeah, DJ.
We can either choose it from the low end of the interval or the high end.
Yeah, so a very common way to do it is to say, let's look at what is the actual rate, say, at the left end of the interval. And for this one, what is it? 28. So if we're going to use the left end of the interval, we would take the actual rate at the left end. And then we'd have that constant rate for the whole interval. Okay? So then what would it be for the next one? 24, 25, something like that. And then we keep doing this. So this is kind of step 2. So step 1 is to determine, and the steps you put on your paper may have, you may have incorporated more steps into one or broken it up further. But maybe step 1 is to decide what our delta x is, break it up. And then step 2, get our constant rates in each interval that are trying to mimic the actual rate of change graph, right? Yeah, Daniel.
I'm a little confused why we're adding these up when this is like already an amount of oil on it.
No, it's not. This is the rate. It's the rate that it's the rate that the area is changing per day. You see?
Okay, but like, doesn't it say it shows the area of oil on the ocean? It doesn't say.
No, so it's the rate of change of the oil on the ocean surface. That's what it is. So it's the rate of the oil on the ocean. It's not the area. It's not kilometers squared. It's this of the oil on the ocean. So. Yeah, and absolutely. If this was the area function, then this process wouldn't make any sense.
Right.
You're right. Okay. Exactly. Okay. Step 1, find the interval. Step 2, get our constant rates that are trying to simulate the actual rate. Remember, this is like the pretend rate of change function. So that's for the first 2 days, say. Okay? Why do we do that? Somebody new. Why is it that we're making this new rate function of constant rates trying to simulate the actual? What's the point of that? Andrew?
So that you can use that rate and multiply it by the delta x
Uh-huh.
times the delta y.
Okay, so what is our goal again? Accumulation of area, right? The quantity. We've got the rate of change and we want the quantity. Okay, and so the advantage to this, Andrew?
Essentially, delta y is just k delta x.
Right, and so what our delta y's are this accumulation of, in this case, what does delta y stand for? Yeah, so delta y would be a little bit of area change. Right? It'd be a little bit of area change. And Andrew said we can calculate that by, so this one right here, let's call it delta y1. What is it, Beth? And what is k? 28 kilometers squared per day times 0.2 days. It's going to give us 5.6 what? Kilometers squared. What does that have to do with the oil slick? Explain what that number has to do with the oil slick. What does 5.6 kilometers squared have to do with the oil slick? Adonijah.
That's going to be that in that area, that little interval of change in x, the rate is going the area is going to increase by 5.6 kilometers squared.
You said in the first 0.2 days, we're approximating. Is it exact or approximate?
It's approximated because it's just based on the interval.
It's based on the constant rate. That's our approximation. So this is the approximate amount of increase in area of the oil spill in those first 0.2 days. Agreed? Yeah, that's what it is. Okay? And if we want the accumulation of oil in the first 2 days, what would that overall, and just in general, in the general sense, what would that calculation look like to find the accumulation of oil, I guess oil area, so oil measured by area. What in general would that, yeah, Helios.
Isn't it the sum of like all delta y's?
The sum of all delta y's. He's offered up the sum of all delta y's. Samantha, what do you think of that? Agree with that? What's that?
Yeah.
Okay, she says yes. Daniel, what do you think?
I agree.
Yeah, so we're each one of these, we could do a little calculation of delta y in each one of these. And each one is the change of, in this case, increase. They're all increases, right? Because the rate's positive. It's the change in the area for each one of those little days. And so if we want the total accumulation of oil area, it'd be like delta y1 plus delta y2 plus delta y3.
So,
Go ahead. And then, so we have a shorthand way of doing that. Remember? Sigma of what would I go to? If we wanted the 2 days, it would be 10, right? Someone had a question. Yeah, go ahead.
your rates then will always be positive unless it drops below. Is that correct?
Yeah, so this particular rate function is showing that what's happening always to the area.
Okay. So even though the rate is decreasing, it's still a positive rate.
That's right. So this is a good point. So what's happening to the rate? It's decreasing. So what's happening to the area? It's still increasing. It's just increasing how? Just more slowly, and now it starts increasing more quickly again. Yeah. It's when, so what would happen to the accumulation when the rate function drops down here? What about your quantity now down here? Yeah, so it would be decreasing when the rate is negative. Down here below, the rate is negative, then your amount of your quantity would be decreasing. Okay, so that quiz won't be graded, but I wanted you to have your own kind of self-assessment of seeing if you're catching on or not. Were you able to kind of reproduce this process? How did you do, Judith?
I did great on this one.
Oh, you wanted to
For
be
the
graded.
first time.
Okay. Well, maybe we'll see. Okay, we'll see. Extra credit or something. We'll see. I'll talk to Owen. All right. Okay, so now would this be a function, or would this be just some amount of accumulation? Yeah, it'd just be the first 2 days, okay? And so now we've also talked about building a function, meaning can we come up with a function that would give us any amount of accumulation over that time? So I could plug in 0.5 days and it would tell me how much is accumulated. can I plug in 1.8 and it'll tell me how much is accumulated. Okay? So that's a more powerful thing, but then it takes more work, right? That takes more work. So far, the way that we've built a function is just by building a table, right? You guys have been building a table. So we could have days. And then you could have area. And so if this was when the accident occurred, what was the area at day 0? You know, that's not always going to be true, right? So there could be a starting amount to the quantity, but if this is when the accident occurred, it would start at 0. And then, so you could build this function just by ordered pairs, right? And what would the area be at 0.2 days? 5.6. How would you get the area at 0.4? Somebody knew. Megan, how could we get the area at 0.4 days? So this one here? Multiply 0.2 by whatever that is, 24. And would that be this right here? This be the area after 0.4 days. She says yes. Andrew next to her.
No, you add the previous day, that just shows you the change in the day.
He wants to add this along with that. So Megan, you want to change your mind or stay with what you said? Because this is, so what is this? This is the accumulation of area, right? It's going to include the changes from before. So to get that next one, it would be the 5.6 plus our new delta y2, right? And then 0.6 would be this whole thing, right? Plus. So this is as far as we've gotten in terms of building the function. We're just building ordered pairs, right? Just building ordered pairs. Okay? But what we want to actually build is a continuous function. So like get a rule that we could plug that number of days in and it'll give us the accumulated area to that point. That's our goal, okay? So in terms of a function, this is all we've done so far is just get ordered pairs. Yeah.
Is that the kind of what we went over, the x minus a over the
That's one piece of building this function, yeah. This is very, yeah. There's lots of pieces we have to put together to get the actual continuous function. This is the first piece. Okay. So I feel like those of you who are participated are getting it. So that was encouraging. So hopefully, I couldn't call on everybody, but hopefully as a class this is making sense. Anybody have a question? So similarly, this was your task for the homework. Let me just throw up see if this is, so we said the intervals, again, intervals were 0.2, and it instructed you to use the left sides of each interval. So first of all, did your simulated rate function look like my blue one there? Okay? And then, what was the time? An hour? Was this hours? Yeah. It's hours, okay? So then hopefully you put together this function based on some ordered pairs of distance traveled, and so this is the input, this is the number of hours, and then this is the output of the accumulation function. So when I did it at 2 hours, I got distance traveled of 61 miles. Did you get something close to that in the ballpark?
How much is ballpark?
55 to 65.
Okay, pretty close.
Okay.
A little bit outside.
Yeah. Questions on your homework? Yeah, Nicole.
How I set up the table was I didn't change the delta x over delta y, so instead of adding each one, I only put the actual delta y between the 0.2, so 0.2, 0.2, 0.2, and the corresponding change.
So you just graph the changes.
Yeah, and then eventually added all that. Is that okay? Or would you
Well, it It depends what it's being asked for. If it's asking for a table that's building the accumulation function, the individual changes are not the accumulation.
Right.
They're just the individual changes. So the accumulation means every time you keep adding on the next one. Okay? Other questions on, yeah, Amos?
I do think I did the right side, but I ended up getting 61.7, I think.
Right, so based on, let's hear your reaction to this. He said he actually ended up doing right sides instead of left sides, but you got something similar, very close to 61. So, what's your reaction to that? Why? Or is that okay? Or
Well,
Yeah.
I mean, essentially, it's going to be pretty close because I mean, we're like where you have 55, he would have gotten it for his 0 value, so we would have had all of those same values, and then one more value. And since the value at 2 is pretty close to the value at 0, you would get a very close answer.
yeah, so his first constant rate was like this, but his second constant rate was like this. And then his third was down like this, right? And then like this. So what's happening?
It's the exact same values except for the start point.
Well, oh right, exactly, yeah. So actually, I should have put that even with that. That should have been there. Yeah, exactly.
And his endpoint at 2 would be pretty close to 30. It's just a little higher.
Exactly. So the change that I got for using left endpoints in the second interval is exactly the same as the change that he got in the first interval. You see? Okay, so right versus left. So why not just do it one way all the time? Well, in certain situations it may be more convenient to do one or the other. Okay? But then it's also just a matter of your understanding. Just do you get it? So if you get it, you should have the versatility to do it anyway. So another way that we haven't talked about yet is to talk about doing it by the midpoints of each interval. So look at the midpoint of looking at the actual rate at the midpoint of each. Valid way to approximate? Sure. Okay, so those are the 3 most common. Take the actual rates at the left side, take the actual rates at the right side, or take the actual rate at the midpoint to be the constant rate for that interval. Those are the 3 most common. Just because there's nice symmetry to it. Yeah, Lauren?
Okay, so the blue one is the step function. The blue, what were you?
It's one possible step function. It's the left step function.
And then the purple or pink one, is that the rate of change graph, the function, or is it,
That's the actual rate of change.
okay, actually?
It's miles per hour, right? It's giving you miles per hour at any given time.
And you're just trying to find the accumulation function.
We're trying to find the accumulation function. In order to do that, we need constant rates to make the math easy, right? We need constant rates. So we simulate that actual rate function with our little step constant rate function.
So, but using the left or right, it won't always get close.
No, right. So you might use the right and you might get 59.5. And you might use the mid and you might get 62. Right? Because it's approximating. Right? It depends on what the function
So
is.
just always do what it tells you.
Yeah, or most importantly, be able to do any of the ways, right? Be able to just understand what they all mean and be able to do any of them. Yeah. But know that since we're approximating, left will most likely not equal right, will most likely not equal mid. Okay? But they're all kind of converging on the actual, right? So there is some actual accumulation function, and that's our goal. Okay? That's our goal. What adjustment can we make to create something that's closer to the actual accumulation function?
Take smaller.
Smaller intervals will do a better job, then the resulting step function will do a better job simulating the actual rate function. And if we do a better job simulating the actual rate function, we get a better accumulation function. Make sense? Okay. So let's I want to kind of, if you have that worksheet from last time, well actually, you may have written down, I want to kind of start over with this thing we did at the end of class last time, because I really want to make sure it just doesn't end up being a formula in your head, but really something that you understand. So don't look at your notes from last time.
You mean this one, the left hand point?
Yep, this thing. So let's start over and see how we did. So let's make this say yeah.
Do you have X worksheets?
I do, but not for everybody. I don't have enough for everybody. Can you go make copies of this? Thank you. So, without looking at your notes from last time, what's our goal? To build the actual accumulation function, and we said to do that, we're going to have many pieces and things we have to put in place. It may take us another couple weeks to get this. So here's the first piece. Given a starting point, here's the starting point of 0.75, okay? Remember we talked about this idea of the current value of x. That's what n is, okay? So n is what we're going to call the current value of x. Meaning, if we have this accumulation function, we think about x increasing and taking on all the values from least to greatest. At any given point, we could pause it. We could pause it, and then where we pause it would be what we call the current value of x. So to build a step function, we want to build the left step function. Then in order to do that, we need to know what is the x value at the left end of the current interval. So we have a current value of x, and it's in the current interval. All right, so as x increases, boom, we pause time, we get a current value of x, and we get a current interval. What's our goal? We need to get that x value of the left end of the current interval. So now, just kind of start over. Don't try to remember something that we did last time, but can you come up with the x value at the left end of this current interval? Here, if the current value of x is 9.56, let's make it a little more interesting here. There we go. So we're starting at 0.75. The width of our intervals is 1.62. Your goal, thinking about building a step function, is to get just the x value at the left end of the current interval. Sorry, current interval. If you want a fresh sheet, Owen's got them. Look at that later. I think someone's asking.
Point seven.
Yeah, sure, yeah. Just notice that on your paper. Okay, Stephanie here today? Let's see. Christopher? Christina? Trin? Lionel? Lionel Silk? Wanting Wang? Z Wang? Yeah. Okay. Get someone next to you, explain the process that you did to the person next to you. Share what you did to get this X value. Go. Sure. Eric. Peter. Anthony Ignacio.
I just counted the number of instruments, like 1, 2, 3, 4, 5 intervals. Multiply that. Multiply 5.
I got
Like that interval, like from the first red dot to the red dot. It's 8.1, whatever. This is the number of those at 0.75. Start at 0.75. So that will be the length
Okay, are you ready for a new example? Want to practice something else? Well, let's see. Let's hear. How'd we do on this? Let's see. How about Katie? Can you tell me what you did? All right, let's regroup in the front. So Katie, how did you think about this? Okay, we're going to regroup to the front. So the first thing you did was what? 9.56 minus 0.75. Okay, and why? What does that represent? What does that calculation give you? Or what does it represent? The whole interval. From where to where? To our current value or to where we want? What's that? Current value. So it's the distance, right? It's the distance from the starting point to the current value. Okay? And then what? Keep going. 1.62. So let's keep track of this. She took n minus a divided by what? Delta x. And why? So dividing by delta x, what does that achieve? What's that about? Number of intervals. Okay. What number do you get for that? 5.43? 5.48?
4-3.
4.4. 4.38. Got it. So we'll just say 4.4. How about that? So 5, this is the number of intervals starting here all the way to our current value. Want to keep going? You're doing great. Want to keep going?
Then because we want the left end,
Yep.
we don't want the full interval.
You right?
we use the 5.
You do what?
I use 5 instead of 5.44.
So she came in here and said, we don't want that partial interval. So we just want 5. Okay? What can I do to this formula to achieve that same result? Do you remember? We have a mathematical thing that represents taking it and chopping off the decimal or giving you the greatest whole number that's less than that. Connor.
There's like 2 L's facing.
Yeah, right. 2 L's facing each other. That's what that means. If it's 5.44, chop off the 0.44. Give me the largest whole number that's less than the value in there. That's called the floor function.
The ceiling function with the legs at the top.
Yep.
Huzzah!
Okay, so then you got 5, and then what'd you do with the 5? You're on a roll. Keep going. So 5 times the delta x. And what does that number represent? The distance from the starting to the value we're trying to get. Excellent. Okay. So that's like taking this and doing what? Multiplying by delta x. Are we done? So we got the distance, but we want that actual x value. So to get that x value, we add on a. Okay, and so this is a function. It's a function of what? What thing here are we changing? And calculating left. So this is left of what? What is the thing that we want to be able to change and have it crank out what the left value at the left end is?
It's
N, right? N. It's a function of n. So this is our left function. This is our left function. Given an a, given a delta x, so part of your homework for Monday is going to be to dissect this. So we don't want to just memorize this and use it. We want to understand. So that's why we're taking the time to build it. Okay, where does this thing come from? Anybody have a question? Okay, so how about this? Real quick. We'll start at A as point, say 2. Too small. Try 1, 3. Alright, there we go. That's good. Never fear, right? You've got the left function. So here it is. A is 0.2. Delta x is 0.13. And my current value of x is 6.0767. Find for me what the x value at the left end of the current interval is. What's the x value at the left end of the current interval? Anybody get an answer? From visually, it looks like something still greater than 6. So, but we know it's going to be less than the actual current value, right? So something between 6, looks like it's between 6 and that. Is that what you got? Corey got 6.05. One more decimal place, how about? Oh, it's right on?
That's right.
6.05 exactly.
Yep.
Finding that? Anybody have a question? Doesn't make sense. 6.07. Oh, we have dissension. Let's see, how many people got 6.05? How many is 6.07? Yeah, so there's something's wrong, Adelaide. You got it? Okay, cool. All right, another part of your homework is going to be come up with a command line in Graphing Calculator that, given A and given delta x, will plot all these points in one command line. So I'm going to show you a few things with Graphing Calculator so that you have the tools to be able to do that. So we want, in Graphing Calculator, to be able to, instead of plotting 100 points like this separately, we want one command line that will generate all of those. So I need to show you a few things. So you remember how to just plot a point. How do we plot a point? Control 2, or maybe is it Control Shift 2 on PC? Okay, so that will plot a point, right? Remember Control 2 or do something slightly similar for PC, plots a point. So what I can do is, for instance, I could call the y-coordinate b, and I could do comma, and I could say b, and then if you do option, or which is it? Control equals, you get is a member of. And so here I can specify a set of many values of b that it will do all at once. So I want my braces. And so I could say 0, -1, and 3, say. Not 0, let's do something else here. 0.5, say. Okay, so now it's plotting 3 points simultaneously by keeping the value of x at 5 and giving the 3 different values of y, 0.5, -1, and 3. Okay? If you wanted to do a whole sequence of points, I could do this. I could start at -1 and say I want points every 0.4, comma. So now to say continue like this, or no, sorry. So maybe I want the distance between them to be a half. I want to start at -1 and I want to go up a half each time. So that's not what that stands for. Okay, that's what I mean to say. Okay, so I want to start at -1 and then have my next one be at -0.9, and I want to keep going like that. So you do shift semicolon, I think. Control semicolon. Control semicolon gives you ... meaning keep the list going like this. So what will the next one on the list be? The next one on the list will be -0.8. And then it'll keep going until do another comma. Say up to 3. So how many points will it plot? Yeah, 40 points. So I just made a list of 40 values starting at -1, then -0.9, just like that, up a tenth every time, all the way up to 3. And I want all those to be the y values of these points with x value 5, and so it graphs those. So you're going to do something similar here to graph starting at A and given a delta x to graph points on the x-axis that are going to mark our intervals of delta x. That's, we're going to come up with that. All right? Have a good weekend. Oh, quiz and recitation. Quiz and recitation. As promised.
Mark, can you make that e-things clear?
Which one?